use logs to solve for y here. So if I take the log of both sides, and I'm going to be clever about it, I'm going to take the log base 2 of both sides. This is reaching back to your Algebra 2 and properties of logs, but that's okay. Follow me here. I'm going to take the log base 2 of both sides. And then what happens on the right side of the equation is I've got the log base 2 of 2 to the y. And if you remember, what happens when you take the log base 2 of 2, then that's something that, those are two operations that are inverses and they cancel each other away. So I really just get y equals the log base 2 of x. And this is the inverse of 2 to the x. And actually, it's just by definition that exponential functions have inverses. We see that, and we need a name for those inverses, and we call them logs. Okay? So if you have a base 2 exponential, its inverse is a base 2 log. If you have a base 5 exponential, then its inverse is a base 5 log. Okay, so you should keep this picture in mind. This is what ties exponential and logarithmic functions together. Is that they are inverses of each other. That's something I believe you all saw in Algebra 2 a long time ago. Okay, so we're going to need to be able to graph exponential functions with various transformations, stretched, shifted, reflected, and also log functions with those same kinds of transformations going on. So let me remind you of some quick logarithmic notation. We can make this statement, 2 cubed equals 8, for example. This is something we know is true. What this is saying is that on the function y equals 2 to the x, there is a point 3, 8. Right? So then we know there also exists a logarithmic statement that is equivalent. And this is it. Okay, 2 cubed equals 8 has a logarithmic equivalent that says this. Log base 2 of 8 is 3. Okay? Which is to say that on this function, y equals log base 2 of x, there is a point 8, 3. So think about that for a second. We've got two functions, one exponential, one logarithmic. We have one point on the exponential function, 3, 8, and the point on the log function is 8, 3. This makes sense. So here I've got the point 3, 8. Here I have the point 8, 3. And so that means this property goes both ways. If I have a log statement, I can translate it essentially into an exponential statement of equivalent value. So you practice lots of these in Algebra 2, things like this. Okay, log base 5 of 1/5. What is this? Evaluate this. And then you had to do this little process. Ask yourself this question. 5 to what power equals 1/5? So I say, oh, I don't know. 5 to some power equals 1/5. And then we have two base 5s. 5 to the x and 1/5 is 5 to the negative 1. So that means this equals -1. Okay. So we can evaluate log expressions essentially using this exponential equivalent statement. Right? So we're going to use that translation from exponential statements to logarithmic statements to graph log functions. Okay, here's what I mean. We're going to graph this log function, log base 3 of x. Let's just graph y equals log base 3 of x. How will you know what it looks like? For one, you know that it's going to be the reflection of 3 to the x. This is the inverse of the exponential function 3 to the x. So I sort of should have an idea of what the shape is going to be. But then if I go ahead and choose some x and y values, which ones am I going to choose? What's a good x input to choose there? Well, I'm going to keep this in mind. 3 to what power equals x? So I'm going to choose helpful values for x. I'm going to choose, say, 1. 3 to what power equals 1? 0. And then what's another good x value to choose? How about 3? 3 to what power equals 3? 1. So we should get the hang of this. Another good x input to use is 9. 3 to what power equals 9? 2. So I start to get the hang of what this is going to look like. Now, the inverse function 3 to the x is going to have a horizontal asymptote at 0. So this one is going to have a vertical asymptote at 0. Like that. And I plug in these points, 1, 0, 3, 1, 9, 2, and that should have been kind of predictable how this log function turned out. Why? Because we should know what 3 to the x looks like. 3 to the x is going to look like that right there. So it's a helpful picture to keep on pairing them in your mind, exponentials with logs. So here's 3 to the x, and here's log base 3 of x. I'm going to give you 2 or 3 sort of stretch questions to take these ideas and see if you really understand them. The translation from exponential statement to log statement and so forth. Okay, so you should come into class tomorrow having completed these at least. Okay, the first one is this. See if you can graph this log function . Okay, that is a transformation on the parent function of log base 3 of x. Should you be able to graph this function just by picturing the transformations in your mind? Not necessarily. I would make a table of values for this just to make sure that you understand how these things behave. And then I want you to evaluate a couple of log functions and come into class ready to explain the results that you get. So evaluate this expression here, log base 3 of 0. Evaluate that. And also evaluate this log expression right here. And actually, let me throw one more in there. I'm going to add a question 1.5. I want you to see what happens if you take the exponential function, or the equation that appears to be the form of an exponential function, and see what this looks like. See what it looks like if I take -2 in parentheses, quantity -2 raised to the x power. I want you to explore that function and see what it looks like. Is it an exponential function? Why do you think so, or why not? And that ought to do it.